So you may work on this of up to groups of 4. So I think there are 36 of you, so it comes out to 9 even groups. So if you don't have 3 friends in this class, you will have this by the end of the week. Some people are like, I don't have friends. What I've posted, it's under content, and I have a new one called group assignments. And so what we're going to be going over today is our reduced data path problems. So let me switch over to the laptop here. So it's under content and in group assignments. So I'm assigning it today. It's going to be due a week from today at 9:30. So I've given an example cover page. You can come up with your own unique group name. So, whatever you want to choose it. That kind of, unfortunately in the past, I have to add a couple notes in here. No racially or sexually inappropriate nicknames. That's really awkward to have a conversation with somebody like, okay, come on. You know why that's stupid. And then last year, Harambe was a big thing, so I just made no Harambe nicknames a rule. Keep it relatively short because when you work on the cadence projects, I'm going to be using that to differentiate so you can log in. And there's a group last year, one of the women in that group, she was really excited about a potential NASA project. And she wanted to say, I love NASA, but it came out I sloss Nassers. And so their group name was I sloss Nassers. And so I'll just use that in there. I'll look at the group name. I'll correlate that to where it is in your grades. So I have the way it's going to work. I want it to be handwritten because there's significant correlators between handwriting and remembering for the future, except for part 1 and part 5. So I want to go over this really quickly. So part 1, this is maybe typed. So include a paragraph statement in your own words for each of the following innovators in advanced digital systems. So these are people in the past, Alberto Sangioveli Vinticelli, Mark Dean, and Grace Hopper, who have made innovations in this area that contributed to things that you're learning in class today. What I have found by assigning this is, in the past, I had my PhD student was considering getting out of electrical engineering. And he read about Mark Dean and was inspired by all the work he did in buses. He's also the first African-American engineer to ever hold a U.S. patent. So it's really cool to see things like that. And Grace Hopper, how many of you are familiar with who Grace Hopper is? Okay, so 1. Okay, so the person who's interested in working with the Navy knows who Grace Hopper is. So Grace Hopper is she was a admiral in the Navy. She did a lot of innovations in compiler design, so compiler-driven encoding of the microengine, and she's also the person who coined the term bug, because back when computers were big, she actually went in, tried to troubleshoot what was going on. She found a moth that was causing issues, so she said, oh, this is a computer bug. So every time you call a computer bug, it's because of Grace Hopper. And Alberto Sangioveli Vinticelli, he's now a professor at Cal Berkeley, but he's also the founder of Cadence and has done a lot of innovations in electronic design automation. For being able, all the stuff that you're doing in VHDL and Verilog have a lot to do with this guy. He's made design a lot easier. So part 2, this is going to look somewhat familiar. Translate the C code into MIPS assembly language. So then I have some code here, and just like the example problem from before. So it's a while function, it's an int function, while loop, it has an if statement, and you've worked through everything. So part 3, I want you to translate using the MIPS screen sheet, which may be found under content reference files on Blackboard. I want you to translate everything from that assembly language into machine code. And then part 4, and we're going to be going over this today, I want you to make the reduced MIPS data path that executes the specific instructions. So when I took Advanced Digital Systems at University of South Florida, the instructor just threw up TGO 5.14 and kind of blabbled at us for 3 straight lectures. And guess what? None of us understood it at all. We're like, oh, great, that looks like a spider. So the reduced data path is, can you actually, so some people have photographic memory, some people have a hard time just memorizing things. So I've redone the problem so that you demonstrate your understanding of how the advanced digital system works. And so what we're going to be going over today is what parts do you take out of that data path so you can only need to execute a store word instruction, or only, in this case, I'm going to show you here, a shift left logical instruction. So you're going to draw the reduced MIPS data path for each instruction. And so, but then you're also going to indicate how the instruction's flowing through the data path. And I've got an example here. So at part 5, at the end of your report, I want you to write about the challenges you faced while performing this assignment. Part of this is good for me. It gives me a good idea of what it is that you're struggling with in the material, so that way I can kind of modify my teaching, so that way I can try to help you guys understand better. And part of it is, one thing it's good is in this field is being self-aware, being able to document what it is that you didn't know and what you learned from. And so being able to write that is, and being able to be honest with yourself, and sometimes you can be proud, like, man, you know, this shift left logical thing was really kicking my butt, and I drew it out once and it clicked. So what did you learn? What did you find interesting? What do you still not quite understand? So if I get 9 assignments back and 7 of them say, you know what, I really don't understand branching, I'll probably revisit branching. Remember, fluff is not what's important, so don't just feel like you have to write a lot to get credit for it. You know, just write, be concise if you only have a concise statement. Write this section as though you're expecting a prospective employer to read it. The goal is to show you came across a challenge, learned from it, and were able to learn on your own. Writing fluff doesn't meet that goal. So on pages 3 and 4 here, I have an example. This last page, I have an example of what. So the first instruction in the solution is instruction 100, shift left logical, and you're multiplying j by 4 and storing it in t of 0. It's pretty similar to before. So I went to the MIPS screen sheet, and this is what shift left logical indicates. It's SLL, like we have here. It's an R-type instruction, and that's going to be important in a moment. And then we have RT is the shift amount, and then RD, right? And then remember the opcode and function that was indicated on the MIPS screen sheet. So the opcode is 0, and it's 00 hex. But they turn to be the same length. So they're both 00 hex, but they deliberately code it differently to try to help with avoiding confusion while reading the green sheet. So on the MIPS screen sheet, there's a chart, register, name, use, call, conventions in the bottom right. So in this instruction, A3 is one of the assembler temporaries. So here, A0 through A3 correspond to registers 4 through 7. So A3 is actually register 7. And C0 through T7 are A8 through 15. And so from there, I can actually use this information. So here, the opcode correlates here. RS is 0. Since it's shift left logical and only uses RT and RD, and it's an R-type instruction, then it's going to be zeros. So from the design perspective, you can think, well, we're not using RS, so I don't even need to draw that at all. And I'll show you an example of what I mean. RT equals A3 is equal to 7, and RD is the destination, is T0, which is 8. Shift amount is 2, because we're shifting left by 2, and the function is 00 hex, which comes from this value from the MIPS screen sheet. And so putting that into machine code, you have the opcode, 0, RS is 0, RT is 7, RD is 8, sorry, that's here, sorry. Shift amount is 2, so that comes from this value, and then function is 00 hex, which comes from there. Does that make sense? And so the last thing, and we're going to be going over several examples of this in class today. Okay, you should be able to see this. So I've kind of drawn out a reduced MIPS data path. So the reduced MIPS data path is the portions of the data path that are required to execute this only. So it's an R-type instruction. So we don't deal with data memory. So all this means we don't deal with memory to register, we don't deal with memwrite, we don't branch or jump in this instruction, so that's all gone, right? And so you're just going to increment PC plus 4, like so. You go to the instruction memory, and then you can do this in a way that helps you understand, But what I did to kind of differentiate the difference between what the data path is and how the values are flowing through the instruction are red versus blue. So here I have written out the instruction and the machine code for assembly and machine code. And then what I'm doing is I'm correlating it to what's actually flowing through here. So 00 hex is flowing through there. You see that? RS is 0, but we're not using it, so it's gone. Does that make sense? RT is going to be A3, right? So I have 20 to 16, and A3 goes to RD1. And then T0 is 15 to 11, and it goes to the right register. Since we do not require a differentiating between R-type and I-type in this case, we don't need that multiplexer, right? Because multiplexers are used to make decisions. In this case, we're not making one. So then I've indicated red's right is going to be equal to 1 there. So what's happening here is the 15 to 0 is going to come down here, but 10 to 6 is going to be sent to the arithmetic logic unit. And you see that I have the value of 2 there. The value of 2 indicates that I'm sending the physical value of 2 to indicate that we're shifting left by 2. And then here, the function 5 to 0 is also getting 00 hex. And then I have the ALU control. If you recall, all R-type instructions have the input 10 as the 2-bit value from last class. So I indicated 10 R-type. I have the 2-bit ALU op, and then I have the 4 bits that come from there. On the output of the arithmetic logic unit, I have this register of A3, right? So basically what this means is the value of the register A3 is shifted left by 2. So if you look at the previous section here, if you look at the previous value here, this notation comes from the MIPS screen sheet. So the value of A3 is shifted left by 2. And then that value is then written to write data. Does that make sense how that's going to work? Now, the last thing I want to mention is there's going to be several ways I think you guys are going to try to do this in terms of the clear all, go away. Either you're going to have each instruction come out here on each page, or you're going to have one page with all the instructions and then another set of pages with all of the drawings. Just indicate which is which. So if I'm looking at this one, I should, if you're all of them on one page and it's 100, you should make a little note. This is instruction. Yeah, that's found at instruction memory address 100. Does that make sense? And last thing, and I indicate it here on the assignment. Where are you? Staple this. Must be stapled to be accepted. Of a life rule, happy grader, happy grade. So a lot of you sometimes like, you try to find Lauren because she has a stapler. Staple this before you get here, okay? Because you're going to have a lot of pages on it, and it becomes a mess having to grade that many sheets and all this and put them all together, and everyone's rushing to turn it in. So if you've not found 4 people, or if you're floating around and you don't know anybody in this class, please feel free to send me an email. I will try to introduce you to another group. And one other note, I take every group member doing their share of the work very seriously. In fact, in my syllabus, I have indicated that a form of academic dishonesty is what I call academic bullying, and I've seen it happen many times where you have a group of people and one of them doesn't want to do the work, so he or she finds the student that they can kind of mess with and manipulate the most. And what they do is like, hey, you do that. Oh yeah, I'll get to this sometime, and then they don't answer the phone call, so then the other student gets frustrated and just does that work. So that's why I say passive or active. So If there's a group member who is not doing their share of the work, the process is you confront them a couple of times. If they have not responded to that, that's when you get me involved. And then I will speak to that student, and then in pretty much every case I've ever dealt with, except for one that I can think of off the top of my head, that student suddenly does all their stuff, right? So I take that very seriously. Everybody should be doing their fair share of the work. Now, life can be different. I understand that people work late jobs. There are a few of you who have children in this class, so you have to be able to balance things out. And so if you're in a group, I want you to respect that everybody has different backgrounds, different responsibilities in life. At the same time, everybody needs to step up and do their portion. And don't feel, people can get shy and scared asking about that. Please feel free in that situation, if you've gone to that person a couple of times and they haven't done their work, I'm happy to help out. Does anybody have any questions about the group assignment before I begin lecture? Yes?
If you really want to, can you do it by yourself?
No. Yes. No. You may. I'm glad you asked that. For the group assignment, turn in one assignment per group. So you all work together and you turn in the group. So when we get to the cadence portions, you're going to be able to turn in one assignment per group. Yes.
Can we ask you beforehand, not the day of?
Do you need help?
Yeah.
Of course.
Okay.
Any other questions? All right. So this was the full data path. And what we're going to do is we're going to be going over the control units and how to break it down into reduced instructions. So this is the actual combinational logic for what's going on inside the controller. So what you have is you have 6 opcodes here, and just you all have drawn out wires, right? So all of those are just 6. Now, what's going on here is you have R-type, add-I, load word, store word, branch equivalent, branch not equal, and jump. So here's the trick to remembering this. If you remember from the MIPS screen sheet what the opcodes are, these bubbles are negations, right? You all remember that from 235? So you have, if you have an AND gate, and this is A and B, that bubble means not A and B, right? So the bubbles actually match the values of the opcode. So we zoom in here, see R-type, right? It's 6 zeros. Well, the actual opcode is 00 hex. Comes out like that. Same thing with add-I. Add-I is 08 hex. So it actually comes 00, so that's the first 2 bits, and then 1000. See how that comes out? So if it's a 1, it just goes straight there. So what I have found is that drawing this out, the opcodes, and then drawing it out like that works. So load word happens to be 23 hex. So it becomes 100011. And then the wires just go straight into it. Same thing with store word. It becomes B hex. Yeah, so it's 2B. So that becomes 10, and B is just 11. So it becomes 8, 10, and 11. Branch equivalent is 04 hex. So that becomes 000100. And then branch not equal is 5 hex, 05. And then 000101. And then jump is 000010. So that's 02 hex. All right, so that's the top portion. Does that make sense to everybody so far? And so what we're going to be doing is we're going to be correlating this drawing, what's actually physically going on in the controller, with the truth table that you derived last lecture. So if you recall, register destination is always 1 when it's an R-type instruction, right? So in this case, if all of these values, it's 0, 0, if it's all zeros, then it meets the AND condition. Therefore, the output of the AND gate is 1. So that just goes straight to register destination. In addition, register write is going to be used for R-type, add I, and load word. Not for store word, not for branch equivalent, not for branch not equal, and not for jump. So what we're going to do here is we have this value comes through here all the way to an OR gate. Same thing with add I. Add I comes here to an OR gate. So you OR them together. And then the other one is load word. So you see these go through these 2 OR gates here. So register write is going to be 1 if the opcode is an R-type instruction, or if it's an add I instruction, or it's a load word instruction. Does that make sense? So that's what's going on here with the OR gates. Same thing with ALU source. If ALU source is 0, that's coming from read data 2, correct? So it's not. So it's going to be an R-type. So you see how there's no branch over there? I only want these values are only coming up if I definitely want it to be 1. And this is where the don't care comes into play. If you put this as a 0 or a 1, you'd actually have to add in OR gates to indicate. So what we're doing here by adding in those X's in the truth table, the don't cares, is reducing the size of this. So then last thing for R-type instruction, it goes into, if you recall, ALU op is 1 if you have an R-type instruction or an add I. And the reason why add and R-type instructions are that way is because it's going to be adding. So then for 0, the difference here it's going to be either, if you recall, ALU op 0 is 1 in the case of branch equal or branch not equal, right? So we start with register destination for ALU source. If we want that value of 1, that means we want that immediate value, right? So that's the value. If we want it to be 1, that's where we're going to be having load word. That's where we're going to have store word. And then add I. So we have this 3. So what's actually coming through here, we have 2 OR gates, right? So the first one's coming from add I. The second one's coming from load word. And this third one's coming from store word. And this all goes to ALU source. So we don't want R-type because we're getting it from read data 1. We don't want branch equivalent because we're getting that second value from read data 2, and we're comparing them in the arithmetic logic unit. Same thing for branch not equal. We're comparing those 2 values and putting them into the ALU. And for jump, we're not putting anything into the ALU, so we don't want anything from there, so we don't care. For memory to register, the only instruction we care about is load word. And the reason why is because that's the only time we want anything from the data memory to go back to the registers. So reg write we've discussed already. So the 3 that we use for register write are R-type, add I, and load word. For branch, so I've had 2 signals here. Branch if equal, branch not equal. That makes life simple. We're in this course we would have to continue to add more and more control signals in order to differentiate between BEQ and BNE, which would add another multiplexer, and I trying to keep the data path as small as possible. So what we are doing in the course for the drawing is just branch. For mem read, I only want to read from the data memory in the case of a load word, right? So the load word, so this is mem read, and that's the last value that comes from load word. Mem write comes from store word. And then ALU op 1, we've already discussed. ALU op 0 is going to be 1 for branch if equal and branch not equal. And then last but certainly not least, as I've kind of drawn to try to avoid the OR gates, the only one we go to there is jump. All right, so does anybody have any questions about this? And so that's 5.15. And then I've included here, recall this topical guide objective. So from section 3, we have those 4-bit opcode inputs, and then the ALU out is going to be A and B, A or B, A plus B, A minus B, set less than. So now you're familiar with why the importance of set less than, because you're going to be using it to perform branching operations. And then this is A not B. So using this, our knowledge of this in the truth table from 5.13, we can now design the actual ALU controller. So that's the controller that the previous topical guide objective 5.15 was the controller that we used to send that value from the 6-bit opcode that we draw at the beginning, and we draw that out every time. The ALU controller takes in these function values and ALU op values. Now, recall that for I-type instructions, they don't have that 6-bit function at the end. They use that value for the immediate. So for R-type instructions, every R-type instruction takes in the input of 1 and 0 for ALU op. So now we know how that happens, because everything else is going to be set to 0 except for the opcode that comes in from R-type instruction, because it's 00 hex. It's going to make that AND gate logic 1, and one of the things it's going to do is it's going to set ALU op equal to 1. So all of these instructions here, add, or, and, subtract, set less than, and nor, are R-type instructions. Where did nor go? Okay. Give me a split second here. Since we happen to have this open, we can fill in that TGO by going to MIPS screen sheet. Yes, please. So here we can actually, it gives you a good idea of how we can actually use the MIPS screen sheet. So accidentally, I've come up with a new way to help you guys understand. So in reference files, we have the first thing you'll find is the MIPS screen sheet. And so what your absent-minded professor has forgot to include is NOR. So it's an R-type instruction, so it's there. So we have to look here. So we find NOR on the MIPS screen sheet. It is in fact an R-type instruction, and the opcode is 0, and the function is 27 hex. So here's what that means. We correlate this back to this table, and so this function equivalent is 27 hex. And so that becomes 100111. Does that make sense? That's how these values are derived. So what's going on here? The ALU op is derived in the controller. The value that comes out for all R-type instructions is 10. That's why the opcode for all R-type instructions is the same. So we use a function to differentiate that, because we're sending it to the arithmetic logic unit. So from there, add is 20 hex. So in the 6 bits, it's 100000. And then the output, the 4-bit value that goes to ALU control, is 0010. For OR, it's the same thing except it's 25 hex. And the output that goes to the ALU control is 0001. And it's 24 hex, so it's all zeros for this 4-bit ALU control output. For subtraction, it's 2 hex, so it's 100010 for the function, and then the ALU control is 0110. You see the difference in bit here? Does anybody remember why that difference in bit is important? What do we use that difference in bit for? Think back to the sign. So you're putting that in as the input to the sign bit, which then goes as the input to all the XOR gates. So you can perform 2's complement in the ALU. So instead of having to design an adder and subtractor, you just add 32 exclusive OR gates and use this bit to differentiate. So that's a good example of how to actually reduce the size of the data path and the advanced digital system using intelligent design of your assembly language. Yes?
Are those 4 bits being derived from this, or are they just kind of arbitrary?
Yeah, they are derived logically inside the ALU controller. So it's a much more complex control design than what is in Topical Guide Objective 5.15, so I'm not including it. But basically, it's the same thing. You're getting these values in, it's a set of decision logic. So basically, you can actually use these values. This is 27 hex, right? So that lowercase a just for hex. So what's going on there? You could actually write a Verilog program. They're using a set of if statements where basically the if function equals this and ALU opcode equals this, and you actually can derive you can have a 4-bit output that indicates what's going to happen there. And so what ends up happening is you write it in VHDL or Verilog and then synthesize it either onto an FPGA board or you actually synthesize it down to ASIC. It'll actually derive the logic that's used there for you. So, hey, did I answer your question?
Yeah.
Okay, good. Any other questions on this so far? Yes. Yeah, 2A. So that should be 1. Yeah. So A is actually equal to 10. One zero 1 0. Hold on, you got tools. I said I don't have the same PDF program that I have on my laptop. Okay, well, I'll update that on the lecture notes. But this should be 1010, not 0101, because it's 2A hex. And then NOR is 27 hex, so it should be 100111 here. And then this needs to go away. I didn't mean all of the notes. And then the output is 1100. So for everything else, in terms of add I, load word, store, branch equivalent, branch not equal, and jump, we actually are dependent upon the ALU control because we don't have function value. So everything else are don't cares. And so for add I, load word, and store word, we're actually adding the value. We're adding the value from read data 1, and we're adding it to the sign extended immediate value from the instruction, right? So notice here how these 3 match add. And so branch equal and branch not equal, they have the same ALU opcode. What's going on there is the output that's being sent in is 1000 and 1001. And then jump, we don't care what it is because it's just sending a value out. This could also actually be don't cares. Right? Because what's happening is we don't care what's being added, because when we have jump, we know that the jump value only adds a 1 if that AND gate within the controller, everything else is 0, right? So as a result, register write is 0, mem write is 0, so there's nothing that's going to be updated. Right, does anybody have any questions about this? Okay, so the next set of problems is going to be what you're going to see an example of on the exam. So I'm not going to just have you memorize the data path. What I want you to do is I want you to be able to take the data path, and what's more likely going to happen is I'm going to have an example where you put two types of instructions together, and you have to decide about each one. So to start out here, 6.1 is we're going to draw a single cycle data path that implements R-type instructions only. So what you're going to do is you're going to go through and you're going to think, do I need the program counter? Yes, I need the program counter every time. Do I need instruction memory? Yes. Do I need registers? Yes. Do I need data memory? No, because I'm never accessing the data memory in a R-type instruction. So R-type instructions execute in this way. So we go through, we have no branch equivalent or jump, therefore we have no need for further addressing. So it just simply goes back here to the program counter. Does that make sense? So we go to read address, instruction memory with a 32-bit output here. So this sends 31 to 26 to the controller like always. 25 to 21 is sent to read register 1. 20 to 16 is sent to read register 2. Now, here, 20 to 16 and 15 to 11 in the full data path are sent to a multiplexer with the control signal of register destination. Correct? That's because we need to differentiate between an R-type and an I-type instruction. However, because this is R-type only, I can just take that out. Take it out. It goes to 15 to 11. So that's going to be the right register. And then I include 10 to 6 here because shift left logical is an R-type instruction. And then I put 15 to 0 here, and I just send that. It's actually, you can just write 5 to 0 there to the ALU control. And so you have a 2-bit, it's going to be ALU op here. Does that make sense? And the output is a 4-bit. And then the result comes back to the write data. So that's read register 1, read register 2, write register. This is registers. This is the value reg write. Read data 1, read data 2. Those outputs are there. We don't have any immediate value in any R-type instruction, so we don't require ALU source. We don't require the data memory. We don't require any branching. We don't require any jumping. So does this make sense what I'm asking for here? So what you're going to be doing in that assignment is, when you work in this group assignment, is you're going to figure out all the instructions you need, and then for each one you're actually going to work through what do we actually need for load word, what do we actually need for store word, what do we need for add, and then you're going to add the extra element of you're actually going to indicate the flow of the registers through the data path. And so I've included some notes here This is not required for the topical guide objective, but what I've found is in the past is that students have started to will actually write these out. Do I need this? Do I need that? It's a way to help them out on the exam. So it says down there, there's no data memory, so because there's no load word or store word, also no memory to register, right? So no M2R. No register destination because we don't have an I-type instruction, and no ALU source because no instruction where the immediate input to the ALU is required. All right. Does anybody have any questions about that? All right. So load word. Sorry. So the example 6.2 is load word. So I've given the example here where it take the value from read data 1, add to the immediate value of 16, get that value from data memory, and store it in register S0. So load type, what I have here is program counter like always. I have no branch equivalent or jump, so I don't need to branch or jump in this. Instruction memory with read address and the instruction coming out like normal. 32-bit output. 31 to 26 goes to control. I do need read register 1, so it goes to 25 to 21, and that value is going to come out and read data 1 and go to the arithmetic logic unit. However, we don't need read register 2. We're not reading a second register here. We're going to be writing to the other register. So that instruction example that I had where it was like S2, 16, S0, right? S0 is going to be here, and then the value of 15 to 0 is going to be 16. But I'm not reading from another register. I'm writing to the other register. In this case, S2 is going to be your write register value. So therefore, we don't even need to write anything. Notice how I don't have anything going to read register 2. So in this case, what I'm actually doing is I'm just sending it to write register. Now there's no function in load word, so there's no other input other than the ALU op control signal. The 15-0 is sign extended into 32 bits, and that input is sent to the arithmetic logic unit. So we have S2 and sign extended value of 16 goes to the address, put memread and memwrite. Memwrite is 0, memread. Now convention, I should note something here. Convention, if you just have memread there like that, it could also mean memread is equal to 1. If you want to help yourself differentiate it, memread is equal to 1. It may also be used that way. And then last, we take the data from the data memory, and then we send that back to write data. And that write data value goes to that S0, which I showed in the example problem. Is this making sense? How I'm working through every single portion of the data path and I'm making a decision. Do you actually need this? Do you actually need that? So. And then the little notes here, no input to read register 2 since load word does not require read register 2. No ALU source since read data 2 never goes to the ALU. No memory to register since the ALU output is can never be sent back. So if this was a problem for R-type and load word, you would require memory to register. You'd also require a bunch of other things on the inputs to make sense. For example, it'd be R-type and I-type, so you would need you would need to require register to destination. And you also require ALU source because you need to compare the input of the 16-bit 32-bit sign extended immediate value and read data too. All right, let's go to store word. So it's pretty similar with store word, except we're not writing anything back to the register. So notice how write register and write data don't have anything there. What we're going to be doing, if it's store word S4 16 S0, what's going to happen is I'm going to read S0 here. The sign extended value of 16 is going to be extended to 32 bits and sent to the arithmetic logic unit. Those two values are going to be added, and that gives me my memory address. Then what's going to happen is I am going to obtain the value of S4. That makes sense? That value is going to be sent to the data memory and written to the address that's calculated here. So this is S4, and that address is the base address of the pointer in S2 plus the offset of 16. Just like normal, I have PC plus 4 in a normal loop. Instruction memory as normal, 31 to 26 goes to the control. 25 to 21, read register 1. 2016, read register 2. No write register, so therefore I don't want to write it. No write data, so I don't write it. And then ALU control has the 2-bit ALU op value coming in, because that's generating that value that requires the 4-bit output, which is 0010, which indicates it wants to add. All right, I'm going to move on to the next problem. So this one is an example of when we're combining load and store word. So 6.4, draw a single cycle data path that implements load word and store word instructions only. So now you need to think through about each portion and think about it in terms of 2 instructions instead of just 1. So we don't have branch and jump, so the simple value is there. PC plus 4 goes right back. We have the read address, immediate, and instruction, as always. We have the 32-bit output. 31 to 26 goes to the control signal. Now, every time, 25 to 21. So what I would do here is I would actually draw out, I'm going to put red for load word. I'll put blue for store word. I'm going to use the same registers so you can see the difference, okay? So for both of these, S0 is going to go to read register 1, right? So for blue, it's going to come out here, and it's going to go there. And for red, so far it's the same, right? Because that's the base address of the pointer for both of them. Now, for load word, I'm taking the sign immediate value and I'm adding it to get the address. Sign extending it, putting it there. For store word, I'm doing the same thing, right? So I'm adding the offset here. So what the difference is where I'm going to write it versus where I'm going to store it. So register write is going to be, we need reg write because it's 1 if load word, right? 0 if store word. So I need register write. And so for load word, what I'm going to do is I'm going to write to a register. So 20 to 16 is going to go to, I'm just determined to get rid of load word entirely here. So load word is going to go 2016 to the write register. It's going to calculate this value of the address. Memory read is going to be 1. It's going to get the value from read data and write to the write data, correct? Here's the difference with store word. So store word is going to read the value from read register 2, and it's going to take that value and it's going to write that data to data memory. Mem write is going to be equal to 1. In this case, both ALU values of the control signal are going to be the same because what load word and store word are actually doing are they are adding the base address from read register 1 and the offset, the immediate value from the instruction. So the design choices I made here, we don't need register destination because there's only one register, there's only one instruction that requires writing to the registers, correct? And that's load word. So we don't need that. We don't need ALU source because I'm never taking the value from read data 2 and writing it to the ALU for use in a calculation. I don't need memory to register because I'm never taking the ALU output and potentially writing it back to the registers, correct? So memread and memwrite, I do need both of those because I'm doing a load word or a store word instruction. I need register write because load word needs register write to be 1, and I do require the 2-bit ALU op value. Is there any questions on that? I do want to get to this last example, 6.5. I think, yeah, we'll spend the last couple of minutes going over this example here, and then I'm going to dismiss your class. This one is R-type and add immediate. And the video will be posted so we can go back over and look at these in detail. PC+4, read address, immediate from the instruction memory, comes out of the instruction. So 31 to 26 always comes through here. Now, R-type, S5, S1, and S2. And then add I, S5, S1, and 4. Right. So for immediate, add values, I need this read register 1 to go to the arithmetic logic unit. For read register 2, I get the value from read register, and it's going to go here. Now for immediate, I get read register 1 as well, but I need this 16-bit sign extended value to go here. So I do require ALU source because I need to make that decision. So you have 0 or 1. 0 is the input from read data 2, and 1 is the value of the sign extended value. For add, I also need the function value. I need 5 to 0 to be sent to the ALU control. I have that 2-bit ALU op every time. Also, so it is an R-type. So for R-type instructions, I also require 10 to 6 because shift left logical. For I-type instructions, I need to decide whether or not to write register here. So that's S5. Or, so that's 15 to 11 for S5. And then add I need that for here. So that's what I'm determining. I also need reg write because I'm writing to the registers in both cases. And then write data is going to come from the output of the ALU there. All right, so does anybody have any questions about this, how we actually take the data path and we differentiate between them? And how we go through and we actually make good engineering design choices to reduce it? All right, so on that note, I'm dismissing the class. I will also be over there. I pop my head into basically, this is where you have the opportunity to leverage your professors to help you. So we tend to stop guys. So if you're talking to an employer and I see you, there's a good chance I'm going to go over there and you get to see me glad hand and tell them that you're the best thing since sliced bread. They should give you a lot of money. So, and C Spire, Xavier Pittman, former student of mine. back in the day, I was the one going over hey, you should hire Xavier. So just tell, if you see him, he has dreads on a beard, good guy. If you see him, Xavier Pittman, tell him Dr. Morrison said hello and that he should talk to you.